Okay, in our first week, we had some introductory discussions, and so we did not have very good progress on our actual uh, lectures or whatever we had in our lecture note. So, but probably today we can move faster, and you can hear me fine, right?
Yes, sir.
Okay,
Yes, sir.
thank you. Okay, so I think we have enough people already, so we can go ahead and begin our discussion. So we are discussing how the correlation might be done. Uh, you work with a particular PN sequence. So that's a sequence given or it's known, and then you work with some other codes that you are receiving, uh, and it may be you may be looking for the same code. Okay, so you want to have uh, the reception with the same code, and the starting point of the code sequence you want to identify. So for this purpose, correlation is done, and uh, when you actually already converge with the same code, then autocorrelation will help you identify the starting position. This is what we could see here. So we work with the same code, and so then it's autocorrelation. And we found the correlation peaks. The peaks will always be 1, okay, but the other values should be very low. And this is a perfect case when the other value is the has the lowest possible values. Uh, and at all other stages, we had the lowest possible values. So all other, as we went through the rotation, we had the lowest possible values. So as we discussed that in the corrupted situation or poor reducing quality conditions, both of them, because of bits in error, both of them can deviate from their actual position. But when you have the largest separation between the peak and when you have the smallest values for other states, then you are in the best position. You have the least chance that you will end up with a erroneous detection. Uh, okay, although it's a poor radio link quality condition. Similarly, if you work with a different code, then it is cross correlation. Like here, we have two different codes, but in this case, you have two purposes. First, you want to, uh, okay, well, maybe you want to find out which one among a few codes is the is actually your code, okay, or matching with your code. You know your own code, so but you receive a few different codes, so you wanna find out which one is matching yours, or actually uh, which one is your own code. Okay. So cross correlation works the same way. You keep rotating and you keep finding out the values, and if you have good cross correlation property, then of course in this case, as I use the term family. Okay, well, that you work with the different codes from the same family, from the same type of s- circuit generation. Okay, the circuit structure will be the same for all different codes generation that you have in the air. So the other codes to we can call to belong to the same family. And if you have good cross correlation properties for this particular type of code, okay, or type of circuits that you are using, then uh, for any of the rotational position, okay, as you keep rotating the other code and finding out the values, you will find out this kind of low values. Okay, it may not be the lowest value always, but it should be pretty low, or the lower it is, the better the cross correlation property. Okay, and there shouldn't be any peak because you have a different code. So in the case of cross correlation, you don't expect any peak. Okay, so correlation peaks mean peaks appear when you, in the case of autocorrelation. So you expect the low values, and as you complete the rotation but find no peak, then you can conclude that it's a different code. It's not the same. And so you try with another code then. Maybe you have received 3 or 5. So one by one you try, and you stop when you find correlation peak. Then you decide that it is the right code, is matching my own code, and I have also actually found the starting point of the same code. Okay, both of them you find out together. Now, if you have the perfect cross correlation relationship among the different codes of the family, then you call them to be orthogonal codes. And we have an example of them. These two codes are orthogonal. Now you see that I mean uh, when I mean if you do XNOR operation, okay, let's work with XNOR, XOR or XNOR, whatever. I mean you could use any of them, but let's use XNOR. So when you match, you have 1, and when they don't match, you have okay. What was in XNOR? In
Sir, if
am I
if a
right?
signal input is 1, then the output will be 1. Am I-
It's XOR or XNOR?
Sir, it is XOR.
It's XOR. Yeah, sorry, I was. Okay. So I mean, one of them you need to use either XOR or XNOR. This example is XOR. Okay. So when it is not matching, you have 0, but instead of 0, let's use -1. Okay. This is -1 in place of 0 because that will help us demonstrate more clearly, okay, how you're removing the impact of wrong codes. Okay, you wanna keep the right code only. uh, Remember the example that in the party you have sound from uh, many speakers using different languages. Okay, so you wanna uh, I mean get rid of all of them. Okay, you have the sound coming to you, but you wanna have a condition that you don't have really impact. Okay, on the detection of your particular speaker. Okay, who is speaking in the same language. So with -n we can show it more clearly. Okay, now you see, as you sum up, okay, after, I mean, when you have cross correlation 0, okay, I mean, orthogonal relationship means you have 0 cross correlation, then uh, with I mean, if you sum up all the different values, okay, you get 0. Okay, 2 minus 1 and 2 1. So as you sum up, you get 0. Okay, but you know that if you had all, if we use the same code, okay, same code, then we would get the same values. We would get 1 for all of them. I mean, in place of this one, do I have that example? Okay, I have that example, but after the spreading operation. Okay. Let me just, I mean, we can visualize if we had the same code, then we would have 1 for all of them. So that would give us correlation peak. I mean, it would be 4, okay, as opposed to 0 here. Now, the way you send the data, actually, you need to send some data. In the CDMA system, every user will be assigned a particular code for communication. When you are in idle state, you don't have any. But as you in the case of 2G, probably I mentioned that you when you start the voice call, we'll also show it in our lab class. Okay, using real tests. That when you are setting up a voice call, right before the voice call, you receive a message from the network. It's called the name of the message is assignment. That gives you, as we open the message, okay, you'll find that there are quite a few fields in the message, but one of them gives you the frequency number. Okay, we spoke of ARFCN, which indicates the 200 kilohertz frequency. All the possible 200 kilohertz frequencies are actually have some corresponding ARFCN. So that ARFCN number is included in this assignment message. Also, you'll be using a particular time slot out of the 8 uh, I mean available slots. So it also gives you the slot number. Then I mean they are numbered from 0 through 7. So your message may show you 4, 5 or something. So from then on, the UV starts using that particular slot, okay, for operation. Similarly, when you start sending data, okay, either for voice purposes or for some data purposes, uh, when you start sending data, you receive a code from the, I mean, in CDMA network, you receive a code from the network. Before that, when you were in idle state, you had no codes assigned. Once you get the code, I mean that I mean you have it unique. No other guy in the same cell will have this particular code. Okay, but you need to send some data. Okay, so far we have been talking about only codes. That using code you have the orthogonal relationship and all that. But what the heck with the code? You if you send only the code, it doesn't help. You need to send some data. So how do you do that? What do you do? You have some data like here. This is the data for you. Say 5 bits you wanna send. So then you multiply your data with your code. Okay. Again, multiplication means XOR or XNOR, whatever. Okay. But okay. So you multiply the I mean your code with your data with your allocated code. So in this example, this is this 4 bits code. I mean, okay, none of them. Okay, this 4-bit code is given to you, and we are using some orthogonal code in this example. So other people will have some code which is orthogonal with us, with ours. So after you multiply, I mean, when you have -1, your code will be just be flipped. Okay, which is 1, you have the same code sequence. So you you get this string then. Okay, so instead of this string, uh, I mean 5-bit string, now you have got 20 bits string, and then you transmit this one. Okay. So your transmission will look like this. Okay. This is the digital data you send. Of course, I mean there are further processing. Okay, finally you uh, modulate on a carrier. Okay, the final transmission is always analog. Okay, but the information you have, uh, I mean, this is the early stage you are processing your information. So you have digital states. Okay? So now you put this one probably -1, then 1 1, then -1. So on and on you have the whole string. So this is what you are sending. At the receiving end, well, now other people, okay, will be using the same frequencies at the uh, same time, but they will have different codes. Okay, well, the base station needs to be able to distinguish. It needs to say retrieve your information, but the base station is also receiving data from the or transmission from somebody else. So how the base station can receive? Well, the base station is receiving what you are sending, the same string it is receiving. The base station must know what your code is. So it knows that this is the code. Okay. So, so as what it does, it again performs the same operation with the reception. Okay. So when you, I mean, by same operation, I mean XOR operation. So, I mean, for, I mean, this particular set, you have all ones. For this set, you have all -1. Okay, because I mean, with this set, I mean, you can actually check. Okay, they all would take on -1, -1, 1, 1, -1. Now the base station can decide what the information bits may be. Well, since I have all ones, then it should be 1. Okay. When you have all -1, they should be -1. Okay. Let me now tell you that in practice, because of poor radio link quality, a few bits may get flipped on the way. So instead of all ones, you may get 3 1 and 1 0. Okay, you have 4 1 bits here. Okay, based on the reception, the base station will decide. So it may happen that you have 3 1 but 1 0, but then the base station after polling may decide that it is 1. Okay, okay. So this type of okay. So in practice, I mean, the sequences are longer, and even if some bits are in error, it can still recover. Okay. But anyway, that's actually something I shouldn't mix up here. Okay. How you combat the radio link quality is a different question. Now we are discussing something else. Now, it's let's now consider that the base station uh, works first checks with a different code. It doesn't know, but I mean, which guy is sending this reception. So it knows that somebody else is also transmitting, and he has a code like this. Okay, so your transmission, he checks with that wrong code. Okay, code of somebody else. Now, as he does, now you see, uh, this code is it's not arbitrarily taken. It's orthogonal code. Okay, I mean there is orthogonal relationship between this particular code and this one. Okay, if we did this kind of operation, we would get 0 here. So that tells that it's orthogonal. So once you have orthogonal code, then you see what happens. Well, after the operation, you get 1 1 and minus 1 1. In the case of every set, you will get equal number of 1 and minus 1. So what do you decide? Well, you get, I mean, you are in the middle. It shows neither 1 nor minus 1. So actually, I mean, you must have used a wrong code. Okay, because of the zero cross correlation, you are getting all zeros here. Okay, so you decide that I have a wrong code. Okay, so change your code. Use the code of somebody else, and then you'll find that okay, well, now we are okay. Maybe you have tried this guy for this one first, then you have got all zeros. So then you try this one, and you get this one. Okay, then you decide that this is the right code, and you get the right. You also retrieve the information.
Sir,
Yeah.
I mean, the base station doesn't know which data I am sending. So suppose in this case, for some noise or other issues, maybe some bits get altered. So
Yeah.
then we are supposed to get some ones in the reception. Here we got all zeros. Maybe we got 2 1s and then 3
Right.
zeros.
Right.
Then the base
You're right.
station may think that okay, this is the actual data. Then it may transmit it to me, and then there may maybe error occurrence, sir.
Yeah. You're very much right. The fact is, in real life, these codes are much longer, as we are going to show shortly. Okay, so you will be like we discussed earlier. Okay, this is why I elaborated that part, that you would, in practical environment, the correlation peaks don't you don't get things like this, that you have all very low values and all peak values that you compare and then decide. Rather, because of poor reducing quality, you have, I mean, shorter separation. Okay, but from the separation, you need to decide. You need to decide. Okay. So similarly here, you will get, even when, as I was saying, that even when you are using the right code, okay, you will get. Uh, I mean, some of them may not be actually having the same values. Okay? But you can still decide. Maybe out of say 16, out of 16 you have 2 bits with different state. But 40 for 14 you have the same. So you decide that okay, I have the right code, and also I know what the information is. But in this case, out of 16, maybe for out of 12, okay, you have got the same values. I mean 6 pairs 1 and 6, I mean sorry, uh, I mean 6 ones and 6 minus 1. So that cancel 12. For the rest 4, you may have the same bits. Okay, maybe you get 4 1. Okay, so you consider the situation for the right code. Okay, compare them. So you have here. So as you sum up, you get 4, right? But in this case, you get 14. Okay.
Okay,
So
super
when
question.
you get very small values, so this is why you need good cross correlation property. Okay. The correlation properties are the lower the cross correlation values, the better it is. Okay. We'll also show you that eventually you don't have really perfect cross correlation relationship. Okay. It's not really zero that you can use practically. Okay. At the end, but it is close to zero. Okay. What you're using at the end don't have really zero cross correlation relationship. Okay, because you need to support so many things together, but still it is good enough to give you the right values. Okay, to uh, come to the right decision. Okay, so based on correlation you need to make decision. That's how CDMA works. Now in this case we are considering the transmission of from a single source, and with different codes we are trying to find out that okay, what we have really in the as the information. But in the cell, the the base station will not just receive this one. I'm transmitting this this information. I mean, this is what I'm transmitting, and in our this example the base station is also receiving this one. But we know that in the same cell actually there will be many different users together, so they will also be transmitting, and their signal will be just superimposed, because why, we don't have separate time slots or frequencies. At the same frequencies everybody is transmitting together. So what will happen if you have two voltages together? Okay, at a particular point on the circuit you apply to from two. Okay, they you have to sum up the voltages, right? So similarly, the uh, I mean signal you need to sum up. So let's show how it works. We have here in this example three users, user A, B, C, and they all are transmitting together. Uh, for simplicity, let's assume that we have just 2 bits of information from each of them. Okay, A is transmitting this 1 and -1, B is transmitting these 2 bits, C these 2 bits, and these are the three codes they are using. Of course, they have different codes, and again these are some orthogonal codes. Okay, not arbitrarily taken. Not, I mean, every code has orthogonal relationship with another code. Okay, now let's see how it works. A is sending this guy multiply with its own code. Okay, so what will happen when you have 1, you have the same code sequence, like it is -1 1 1 -1. So you have -1 1 1 -1. Then you multiply with -1, so that will just flip. You have 1 -1 -1 and then 1. Okay, so this is what A will transmit in the or launch in the air. What will B do? Okay, it has -1 and -1, so as you multiply for both of them you just have a, I mean, reverse of its code, and so this is what B has for transmission. For C, okay, is the just repetition of its own code, and it is the code has always -1 value, so you just repeat that twice, so it is always -1 for all steps. Okay, this is what their own transmissions are, but as they launch them together using the same frequencies in the air, they all will get summed up. So now you sum up. Okay. So sum up the values, signal values from A, B, and C. So this is the overall signal in the air now, present in the air. So the base station will receive this signal. Now the base station needs to recover this 1 minus 1 for A. Okay. The information bits for every respective user. Okay, what will it do? So we know the procedure that it say it first wants to. It has of course separate circuit operation to retrieve the information for A, B, and C. So the circuit part, which is retrieving the information from A, is working this way. That it uses first the code for A, okay, and we know what it is, minus 1, 1, 1, minus 1. So we had 2 bits of operation. Data bit, data had 2 bits. So you put your sequence twice, repeat your sequence. Then you do that operation. Okay, the XOR operation. So now you see, okay, do XOR operation, XOR operation. What do you find? Just check from the example. That will help you feel comfortable. Okay. Okay. You see, you had here like minus 3 because of this summation. You had, okay, it went down. It was here minus 1 for all different 3 users. So you had minus 3, and that gave you also plus 3 here. Okay. Now for this part, as you sum up and you average, you get 4, actually 4, and so when you average you get 1. Now what would you get if you have, if you had it from, if you when A transmits with just 1, okay, only 1 bit 1, think about that. What happened then? Okay, like here, what happened? You had just 1, so you recover, you get 4, so when you average you get 1, like, right? The same you are still getting after splitting. You have I mean you get 4 bits, so you have 4 ones, so you need to, I mean, perform average. Okay. On average every bit has 1, on average every bit is minus. The same you are getting, although you have transmissions from other people, you still have the same value 1. It didn't reduce, you have still completely 1, I mean completely the expected values, full 1 you are getting up. The average value is still full 1. Again here, okay, you have completely minus 1. This is the beauty. Okay, but again I mean to address Samir's question, in practice it will not be exactly minus 1. It will be little less because of the corrupted environment. Okay, but it will be but little less than 1, so you can still decide. Okay, so you have 2 things, I mean it will be either 1 or minus 1. So between them it is easy to decide. Okay. Even if it falls little bit or quite a bit from 1. Okay, so the same would happen with the other guys B or C, and probably now you feel comfortable how things work. Okay, so it looks amazing. But think of the example of I mean, the speakers in different languages in the same party. Okay, if you have perfectly orthogonal relationship among the languages, then the language, I mean, the sound from other people shouldn't bother you. Okay, well, it bothers only as a background noise, but not conflicting with the understanding of your language. Okay, probably I'm not sure if I could clarify the point. If the other languages are completely different, then it will not get jumbled with what your peer is saying to you. Okay, I mean, not at all perfect orthogonal. But if the other language is close to Bangla, then uh, it will get, I mean, sort of mixing up. You'll feel, and you can get confused. Okay. So perfect cross correlation property can give you really this type of, I mean, expected values. However, it's true that you I mean, the transmission from the rest, like from B and C, will be some noise. Okay, I mean, you have some energy, unwanted energy in the environment. Okay, like SNR. Okay, you have some uh, energy above which you need to have your actual desired energy. Okay, so it will just work like some energy, unwanted energy. Okay, or like noise. Now the point is, this cross correlation property will be zero, or orthogonal relationship you will get for particular code sequences. And these code sequences you can derive in two different ways. One of them is called OVSF, and the other is called Walsh code. Okay, so the two counterparts, let me write down. Actually, I could type in, but you know what? We have got a nice writing pad, so I just wanna make use of it. So the counterpart. Oh, sorry. Oh, should be okay. Oh, sorry, sorry. I should Walsh code. Okay, and what we uh, would use here is OVSF code. So these are two counterparts. Um, Now there are, two technologies side by side from 3GPP and 3GPP2. Okay, so and they had competition like Coke and Pepsi. So they just took different things, and they, I mean, are always in competition. Well, I mean, Walsh code and OVSF code, they both work with with the same performance. Okay, there's no difference in performance. But 3GPP2 guys first adopted, CDMA, and they used Walsh code. Okay, so when 3GPP guys adopted Walsh, uh, I mean CDMA, they took the other one, not the same. So this is what we have for UMTS. OVSF code. Okay. Um, but let me tell you that both technologies were mostly developed by Qualcomm, and I mean I mentioned it before, and so they had almost equal uh, workforce for the for the two developments, and in they are headquartered in San Diego, in California. There they had 36 buildings. Some of the buildings are very large. So few buildings worked on the 3GPP2 side, and I mean just you have some of the buildings working on the 3GPP side and some working on the 3GPP2 side. That's what they had before. Okay, but now mostly they should have development with 3GPP. So, but previously they had almost equal uh, size in their workforce or all different infrastructure. Okay. So people knew that this building has activities for 3GPP2 and this building has activity for 3GPP. Or whenever a Qualcomm guy first met with another Qualcomm guy, so the first question they had was, which side do you work on, 3GPP or 3GPP2? Okay, let's go back to. So Intel uses OVSF. Now, uh, with say 4 strings, I mean, if you have the code 4 bits long, then there are 16 possibilities. You can have 16 combinations, right? Now, out of the 16, 4 sequences will can have the orthogonal relationship. Okay, you can pick 4 of them with orthogonal relationship. So if you use Walsh code, then you pick 4 out of those 16. And if you use OVSF, then you pick another set of 4 sequences. Okay, out of, I mean, once again you have say ones and zeros, and with 4 bits you want to find out the code. So with 4 bits you have 16 combinations possible. Now orthogonal relationship can be maintained with only 4 out of 16. Only with only 4 sequences you can have uh, orthogonal relationship among themselves. So for the use, okay, that we have demonstrated, only 4 you can choose. But this set of 4 sequences will be different between Walsh code and OVSF code. That's why you have difference between the two types. But if you have say only 2 bits, okay, then you have 4 combinations possible. But with orthogonal relationship, you have 2 sequences. If you have 16 bits long, then there are 16 codes possible as such. Okay, with orthogonal relationship. So it is actually equal to the length of the code. Okay. Meaning that if you have 120 bits long sequence, then there are 120 such codes available who have orthogonal relationship among themselves. Now, how you can find out these bits? Okay, we won't show how it is done in the case of Walsh code. Let me show just the OVSF code generation. What you do, uh, you, I mean, this is the matrix. Okay, you use it. We can put it actually in a very simple way. You put 1, 1, then 1, and then you flip -1. Okay, so put your ones this way, 1 1 1, and then for the right bottom one you flip, which is -1. Then take the two rows. The first row is 1 1, so that will be your 1 OVSF code, and then the second OVSF code will be 1 -1. So you have, you have two OVSF codes possible, and they will be like 1 1 and -1, 1 -1. Now for 4 code, it has to be even number for the length. The length uh, will be some even number. Not only even, actually, it will be some uh, int, integer power of 2, 2 to the power n. Okay. So the next possibility is 4 bits long code, and then what you do, you take this guy, uh, you take the first code from your previous stage. It was, the first code was 1 1. Okay, so take 1 1, again put 1 1, again put 1 1, and then you flip this code, -1 -1. Okay, then take the second code from your previous stage. Okay, the second code was 1 -1. Okay, put them 1 -1, 1 -1, 1 1 -1. Then you flip for your right bottom uh, corner, -1 1. Now you again take the rows, 1 1 1 1 1 -1. Okay, so 4 codes you get on the 4 different rows. So that's how you generate your OVSF codes. So similarly, you should be able to find out the code. If I ask you to uh, find out the codes with say 8 bits length, then you should be able to do that, right? You will take these 4 codes one after another. First take the first one, okay, put them with the same values for 3 positions, and for the right bottom you flip the whole thing. Then you take the second string, then you take the third string, then you take the fourth string. Okay, so this way there will be 8 uh, codes generated, each with a length of 8 bits. This is one 16 bits long OVSF code, and this is your data. When you're sending -1, what you need to do, first you multiply the data bits. You have to multiply with your code, and then you send whatever you got after multiplication. This point we need to highlight now. We have you had just 1 bit for transmission. Okay, like we showed in our early examples, we had just 1 bit for transmission, but actually you are sending 4 bits instead of 1. So the actual transmission in the air has higher number of bits, and a lot higher. Like here, it is 4 times. And when you use 16 bits long code, it will be 16 times more. Okay, instead of your 1 information bit, you need to transmit 16 bits. So this is called spreading. Okay, you actually spread. You increase the number of bits before transmission. You really transmit, uh, I mean, so many, so many bits. Okay, increase it, multiply it by a large number. Well, we also discussed that. Okay, uh, so this is why the term we had before, like spreading. Okay, and when you are using this orthogonal code, it is called orthogonal spreading. So the term spreading, uh, we now start using, and the length of code tells you the factor by which you spread. Okay, like here, you spread 16 times. You increase the number of bits 16 times. So this is called spreading factor. The spreading factor, or SF, is 16 here. And the term OVSF has actually, I mean, it's orthogonal variable spreading factor. So it's 16.
Sir,
Yeah, yeah.
sir, here you are saying that we are introducing, sir, 16 bits for one code, sir. So, sir, I think, sir, there might be also a disadvantage that, sir, won't be there any, sir, bit error rate that may be high, sir, in this case. So, why are we using, sir, such types of techniques?
Well, it doesn't relate to bit error rate directly. I mean, the bit error rate depends on how corrupted your environment is. If you have a wired transmission or some perfect medium for transmission, then you should have most of your bits correctly received. Okay, that, I mean, the number if you increase the number of bits that you are sending, that does not increase the likelihood of errors in the bit. The likelihood of error depends on the link quality. Depends on the link quality. Okay, but of course it's a big problem, or you are bringing some major disadvantage as you increase the number of bits. You need to send one bit, but instead you're sending 16, or I mean, to transfer one bit of information, you need to now transmit. You need to transfer 16 bits. So that's a, I mean, that's an inefficiency. That's an inefficiency. So the disadvantage here is inefficiency. Okay, not increasing the likelihood. And 16 was an example that you barely use. In the case of voice, um, typically the spreading factor is 128. Okay, 128. So instead to send, I mean, you increase 120 times before transmission. So the system is made so inefficient. Okay, but you have to do that because, I mean, uh, the different users. Okay, I mean, it will be shortly clear. I mean, there's the part we need to discuss. Well, I have already come on to for. Uh, I mean, that part I have come on to already. But the point is, you have to simultaneously support so many users. It's multiplexing. In the cell, there will be so many people, and all of whom you need to support together. So you need to allocate different codes, and so that inefficiency you need to actually live with. Okay. Well, let me I need to talk a little more about the OVSF codes now. See, we are we know how to generate, and that's like some branching, right? So we had two codes from when we had 2 bits long codes, and from these two we generated the, I mean, the 4 codes. Okay, each of them had 2 branches, right? I mean, this one we put here, and then we got 2 rows. Similarly here, I mean, for the next stage, you'll take the four, I mean, one on one, and you'll put them. You'll get again 2 rows, okay, leading to 2 codes with longer. length. So you have some branching like this, and it's like a tree. So that we can also show this way. And as we go to lower levels, we have longer code length, or the spreading factor is higher. Okay. Now, the orthogonal relationship can be maintained only when you don't use you don't select the codes from the same branch, or uh, from the um well, how I should put, if the point is, if you pick a code, you cannot pick its any code which you have in its lower levels in the uh, as you branch more. Or if I put it this way, if I use the term parents and children, then it will be easier for explanation. Like if I say that the lower levels are like children, okay, and then you have grandchildren or something. So if you select a code like this guy, okay, the yellow blue marked codes are in use, or they're selected for use. So when you select this guy, then you cannot use any of its children. If you select any of its children, then that will not have orthogonal relationship with this one. I mean, you have selected this one means that you have assigned it to somebody for use. Somebody is using this particular code for transmission. In the year, there will be transmission with this particular code. At the same time, you cannot have the use of any of its children, because if you have that, I mean, the children will not have orthogonal relationship with the parents. Okay, so like here, I mean, these two, I mean, uh, all these 8 codes have orthogonal relationships among themselves, but with the parent they don't. Okay, so the blue marked, I mean, this all these 8, if you assign to different people, it's okay, there will not be orthogonal relationship. But for this guy, you wanted to pick from this level. Okay, you assign this code from this level. Now you need to stop. Don't find out its branches for allocation. Just stop. So don't expand the tree. So it's a tree, it has branching, and whenever you pick anyone for use, stop branching from there. Its children or grandchildren, none of them can be used. Now, the final transmission rate has a fixed value, and that is like what you send after spreading. Okay, after spreading, the CDMA guys is called chip. The term chip is used here, although I mean it's nothing different from bit, but for I don't know why they use the term chip, and only CDMA guys use this term chip. So after spreading, I mean, it's I mean, in your understanding, treat it like bit, but just we need to call it chip. The CDMA has a fixed rate of transmission, 3.84 MCPS. Okay. You know what? I love to use the writing pad. So 3 point MCPS. So that means 3.84 into, there is some delay. So the the app that we used in the last class had less delay. Okay, from next time we'll use that application. 3.84 into 10 to the power so chips per second. Okay, quite a bit of delay with this application. 3.84 into 10 to the power 6 chips per second is a fixed data rate for transmission. Fixed rate. Oh, lot of delay. Man. So everybody uses the same rate. Okay. And the analog bandwidth you have normally, the way the technology state we had then used the type of filtering that they used is called Nyquist filtering. That part we won't discuss, but that shows that with Nyquist filtering you have the actual bandwidth little larger than the digital data rate. There is some uh, I mean 1 plus alpha value. Okay, so anyway, with that you need to multiply, but anyway, so it is little larger, and so 3 point little larger value from 3.84 mega is 5 megahertz. So you have 5 megahertz for transmission. So everybody use 5 megahertz for transmission, and the digital data they have is fixed 3.84, because when you have the bandwidth fixed, the digital data you also need to keep fixed. There's direct relationship. So that's fixed at 3.84 mega chip per second. Now you see, you have some information bit. Okay, maybe say you need to transmit 10 bits. That's your information. But you multiply that with your spreading factor, and then you transmit. Okay, so that gives you how many bits you are sending. But this whole thing has to have a particular rate. So if you divide it by second, then you have a fixed value 3.84 into 10 to the power 6. So the right side is fixed. The number of bits you are sending has to be multiplied by spreading factor before transmission. So per second, how many bits you are sending will then be fixed. That's 3.84. After spreading, whatever you are sending has a fixed rate. Meaning that if you have higher spreading factor, you can send more information, right? Right? If you increase your spreading factor, then you can send more information, right?
Yes, sir.
But actually, at the end of this long class, you have got, I think, you have lost your attention, and so you said, yes, sir. It should be the other way around.
Mm.
if you increase your spreading factor, you actually need to have less information because their multiplication has a fixed value, right? Have you got back your attention? If you have a higher spreading factor, okay, the
So if we have higher spreading factor, less information will be converted to big stream of data, right, sir?
yeah, you can send less information, right? So the spreading factor, if you increase it from 16 to 128, then you see, I mean, your number of bits has to be maybe I take the example from, if my spreading factor, I change from 16 to 32, okay, I make it double, then of course the number of bits that I can send per second will has to be just halved because their product has to be fixed, right? Got it? So
Yes.
the ratio that you use to change your spreading factor, okay, will also change the information rate that you use for transmission, but in the, I mean, in the reciprocal way. Okay, you increase the spreading factor, so for voice, as I said, that your spreading factor is 128, but that will not be a problem because the data requirement for voice is very low. So your information rate, the rate at which you are sending your information, has a low rate, but that's sufficient for your data. However, for FTP data transfer, you see, you have a spreading factor of 8. Typical, these are typical values. Okay. Even for voice, sometimes 64 are used. Okay, typically voice uses 128. For data, typically 8 is used for FTP transfer for this type of high data requirement. So for I mean, then your data rate will be pretty high. However, what is the problem if I give everybody high spreading, I mean low spreading factor? Everybody can enjoy high data rate. What is the problem with that?
So
Well,
error rate increases.
error rate will increase. Yeah. I mean, that also shows that you have got distracted, because I was saying that the number of bits that you are seeing, all we are thinking about, we are talking about uh, spreading factor. Oh, sorry. Uh, you some noise you must be hearing. Okay.
Yes, sir.
Yeah, it sounds like some helicopters are flying, right? But actually, it's the gun from City Corporation to kill mosquitoes. Okay. The City Corporation uses tanks to kill mosquitoes, and that hampers our classes. Okay. So, as I mean, it's all about the number of bits that you are sending, and it's no way related to the likelihood of errors. The error rate is no way related to how many bits you are sending. Okay. So, I mean, the choice of spreading factor has no bearing on your error rate. Then what does it affect? Well, it affects how many users you can support in the cell. As I said, that if you select a particular user, particular spreading factor, you cannot use its children. Now you see, a lower spreading factor can give you a better data rate, but when you allocate this a low spreading factor 8 to a guy, you need to stop the number of, you cannot use its children. So you will lack the number of cores available. As you go to lower and lower values, you have higher and higher spreading factors. So a particular user will have poorer data rate, but you can support more users simultaneously. At the same time, the higher number of users can be supported. Or you can put it this way, that the overall data rate is the same, but you just apportion. And how you do that? Well, for some people, you may allow them to enjoy high data rate by assigning a low spreading factor. But that will be a big sacrifice. When you say for this guy, uh, if if instead of allocating spreading factor 4, if I continued branching and I continued up to 64, or maybe just up to 32 level, okay, then here I would get, okay, from this level, you know, this instead of one guy, you get 8, right? From this level, you would get 8. So 8 more users. Instead of this one guy, you could support 8 users in the cell at the same time. So instead of, when you are allocating spreading factor 4, you instead of allocating 8 people with spreading factor 4, spreading factor 32, you are allocating this guy with this privilege, spreading factor 4. So the lower the spreading factor, the more privileged that particular guy is, but blocking the possibility of uh, the use of many other people, okay, or blocking many other users operating at the same time. So in practice, you have even spreading factor up to 512. The possible ranges. With that, I will stop today. For downlink, the possible spreading factor by specification ranges from 4 to 512, whereas in uplink it is up to 256. Okay, so the spreading factor can vary, and the higher the spreading factor, the less privileged you are. When you allocate, you are assigned from the network will assign. When you are assigned a high spreading factor value, don't be happy that you have got a very high value. Okay, rather you will be able to use a low data rate, but you can be happy thinking that many other users can now use because of your uh, because you are poor, so many other users can now have money. Okay, so many other users, if everybody is allocated 512, then 512 users can be can enjoy. Okay, if all people are allocated 32 level, then 32 users can be supported. If you just allocate 4, then only 4 users can be supported in the cell. A particular cell can have only cell if you allocate 4 to all of them. Okay, I think I should have stopped a little bit earlier and made the floor open for questions. Any questions?
No question, sir.
Sir, up to this slide number 7, sir. Can you, sir, briefly summarize, without going to technical details, what are the things that we've learned so far from slide 1 to slide 7? It will help us to grasp the overall thing without going into technical details, sir.
Okay, do you want me to do in the next class or now? If I understand you correctly, you want me to sort of summarize what I have discussed so far, right?
Yes, sir. Like first আমরা correlation, then spreading, then orthogonal, then how data rate is related to spreading. Sorry, to summarize, I mean,
Okay.
I don't need to go into the. We don't need to go into the technical details. Just a little summary. Overall
Okay.
technology.
Okay, that I can do in the beginning of the next class. Sounds good?
Yes, sir.
Okay. We have a class tomorrow, so I'll do it then. Anything else that I can help you with? Okay, if not, then I'll see you tomorrow. Thank you for your time.
Assalamu alaikum, sir.
Assalamu alaikum, sir.
Alaikum assalam.
No.
Alaikum assalam.